What if humanity's future does not unfold on Earth at all? What if the next chapter of our species is written on the moon's regolith, inside the rusted soil of Mars, or beneath the frozen oceans of distant moons? This is not science fiction. It is a timeline already in motion. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we explore the future of humanity, science beyond Earth, not fantasies, not myths, but real missions, real technologies, and real scientific constraints that will decide whether humanity becomes a multi-planet species or remains bound to a single world. Humanity has always expanded by crossing frontiers. Around 70,000 years ago, Homo sapiens began migrating out of Africa. By 1000 BCE, humans had crossed oceans using celestial navigation. In 1969, a human footprint pressed into lunar soil at Mare Tranquillitatis, marking the first time life from Earth stepped onto another world. That moment, on July 20th, 1969, was not an end. It was a beginning that stalled. For more than 5 decades after Apollo 11, humans remained confined to low Earth orbit, circling the planet aboard space stations at altitudes of roughly 400 kilometers. Meanwhile, Earth itself entered a period of unprecedented stress. Atmospheric carbon dioxide surpassed 420 parts per million by 2022. Global biodiversity declined. Resource demands increased alongside population growth. Science began asking a hard question: is Earth enough? Earth. The modern push beyond Earth is driven by survival, science, and inevitability. First is planetary fragility. Earth is resilient, but not invulnerable. Geological records show at least 5 mass extinction events over the last 540 million years. Asteroid impacts, supervolcanoes, and climate shifts reshaped life repeatedly. Space-based observations now track near-Earth objects larger than 140 meters, revealing that cosmic hazards are not hypothetical. Second is scientific necessity. Many questions cannot be answered from Earth alone. How does life begin? Can biology emerge independently elsewhere? How do planets evolve without plate tectonics or magnetic shields? To answer these, scientists must go there. Third is technological momentum. By the early 21st century, reusable rockets reduced launch costs dramatically. Private and public space programs converged, accelerating timelines that once seemed unreachable. By 2024, robotic explorers had mapped water ice at the moon's south pole, detected ancient river deltas on Mars, and confirmed subsurface oceans on moons such as Europa and Enceladus. These were not dead worlds. They were environments with chemistry, energy, and potential. The first true off-world foothold will not be Mars, it will be the Moon. Between 2025 and 2030, multiple space agencies plan sustained lunar operations focused on the Moon's south polar region. This area contains permanently shadowed craters where temperatures remain below -170 degrees Celsius, trapping water ice for billions of years. Water is everything. It provides drinking supply, oxygen through electrolysis, and hydrogen for rocket fuel. A lunar base that uses in-situ resource utilization transforms the Moon from a destination into infrastructure. Scientific objectives drive this phase. Lunar geology preserves early solar system history, erased on Earth by erosion and plate tectonics. Instruments placed on the Moon's far side offer radio silence ideal for studying the cosmic dark ages, a period before the first stars formed. Human factors research also accelerates here. Long-duration exposure to 1/6 Earth gravity allows scientists to study bone density loss, muscle atrophy, fluid shifts, and neurological adaptation in ways the International Space Station cannot fully replicate. The Moon becomes a testbed, life support systems, closed-loop recycling, radiation shielding using regolith, psychological resilience in isolated environments. Every failure here is survivable. Every success is scalable. Mars changes everything. Mars is not Earth's backup. It is Earth's opposite lesson. Around 4 billion years ago, Mars possessed rivers, lakes, and possibly shallow oceans. Geological evidence from Jezero crater shows delta formations created by flowing water. Then Mars lost its global magnetic field. Solar wind, stripped its atmosphere. Water disappeared into space or froze underground. This history matters. It tells scientists what happens when planetary protection fails. Human missions to Mars, projected for the 2030s and 2040s, face extreme constraints. In one-way travel times range from 6 to 9 months, depending on orbital alignment. Surface radiation levels are roughly 40 times higher than Earth's average. Gravity is only 38% of Earth's. Survival requires adaptation, not terraforming fantasies. Early habitats will be buried beneath regolith for radiation shielding. Energy will come from nuclear reactors and solar arrays hardened against dust storms. Food will be grown in controlled hydroponic systems using recycled water and carefully managed nutrients. Mars colonists will not be explorers in suits. They will be system managers. Biologists, engineers, medics, and psychologists maintaining fragile ecosystems inside pressure walls. The scientific payoff is profound. If biosignatures are found in ancient Martian sediments, it would confirm that life can emerge independently on multiple worlds. That single discovery would reshape biology forever. But Mars also delivers a warning. Planetary habitability is temporary. Protection matters. While Mars captures public imagination, science looks further. Europa, a moon of Jupiter, hides a global ocean beneath 20 to 30 kilometers of ice. Tidal heating provides energy. Chemical interactions at the ocean floor may resemble early Earth's hydrothermal vents. Missions planned for the 2030s will analyze surface chemistry and ice plume particles. Enceladus, orbiting Saturn, actively ejects water vapor and organic molecules into space. Sampling these plumes allows scientists to study subsurface ocean chemistry without drilling. Titan, Saturn's largest moon, hosts liquid methane lakes and complex organic chemistry. It represents a second experiment in planetary chemistry, showing how prebiotic molecules form without liquid water. These worlds redefine what habitable means. Life may not require Earth-like conditions. It may only require energy gradients and chemistry. Can humans truly live beyond Earth long-term? Biology imposes limits. Human bodies evolved under one gravity, one atmosphere, one magnetic shield. Artificial gravity habitats may become essential. Rotating space stations could simulate Earth gravity, preserving musculoskeletal and cardiovascular health. Genetics introduces ethical complexity. Over generations, off-world populations may adapt biologically to lower gravity or higher radiation tolerance. At what point do Martians become physiologically distinct? Culture will diverge as well. Time delays of minutes to hours break real-time communication. Decision-making becomes local. Identity shifts from planetary to orbital. Humanity will no longer be singular. It will be plural. The future of humanity beyond Earth is not an escape plan. It is a mirror. Every off-world settlement exposes how finely balanced Earth truly is. Every life support system highlights what our planet provides freely. Every radiation shield reminds us what our atmosphere protects us from every second. Space does not save humanity from its problems. It amplifies them. But it also expands perspective. Seen from orbit, Earth has no borders. No divisions. Only a thin blue layer supporting every ecosystem, every civilization, every story ever told. Science beyond Earth does not diminish our home. It teaches us its value. If humanity survives the next 1,000 years, it will be because we learned not only how to leave Earth, but how to understand it. This is Mattermosaic, piecing together the universe, one discovery at a time. If you value science without hype and stories grounded in evidence, subscribe and join us as we explore the universe one discovery at a time. The future of humanity is being written now, not in distant galaxies, but in laboratories, launch pads, and the quiet decisions we make about our place in the cosmos.